Dr. Scott Shue is representing ARPA-E, that's the Advanced Research Project Agency for Energy. And as you will see in his talk, his purpose is to enable transformative changes, essentially, research in the fusion program to try to lower the costs and enable fusion to be available to us in fewer years. It's not going to be tomorrow, but maybe a decade or two instead of the commonly thought of constant of 30 years or 40 years even for practical fusion. Scott was an undergraduate at UCLA and UCE. He went to Princeton to do his PhD in plasma physics. He then went as a postdoc to Caltech and then went for more than 10 years, 15 years?
16 now.
16 years at Los Alamos Lab, where he's been working on an innovative fusion concept. So he has a little bit of practice talking about the subject that he's going to be talking about today. Scott?
Thank you, David. Thank you, everyone. It's a pleasure to be here. Took an Uber from Philadelphia Airport and got here at 2:30 in the morning, but I think it was worth the effort.
Don't tell him.
Okay, so I'm going to apologize ahead of time to move quickly because there's a lot of material to get through. So the title of my talk is What is Needed for Fusion Energy to Impact Mid-Century Power Generation? Here's an outline of the talk. I'd like to give a fusion primer so we're all on the same page about what fusion is. I'd like to quickly discuss the status and remaining challenges for fusion energy development. The remaining challenges are great. And I'd also like to discuss kind of reaching beyond the technical realm. How do we realize commercially viable fusion power soon enough to make a difference? And of course, the most urgent need is mid-century, is driving down mid-century carbon emissions. So we don't have very much time, or no time at all, really. And then I'd like to hopefully get to this point, a little bit of a recruitment pitch for ARPA-E. ARPA-E sends me to universities in part so I can do this little pitch to tell you what ARPA-E is about and also hopefully to get your interest. We have programs from students to postdoctoral level opportunities to program director positions like myself. So a fusion primer. What is fusion? Let's just start with the very, very basics. Fusion is the joining of two light elements like hydrogen or isotopes of hydrogen. And when they fuse, a tremendous amount of energy is released with the reactants. The easiest reaction is deuterium and tritium, two different isotopes of hydrogen. It produces a helium and a very energetic neutron. That's the deuterium-tritium fusion reaction. And just to give you some numbers of how much energy that represents, the fusion of about 132 tons, which is like one train load of DT, would provide enough energy to supply the primary energy, that's 40 exajoules for the entire US electricity generation. And just for comparison, one train car of DT is like 14 million train cars of coal to provide the same energy. And here are some well-known examples of fusion. The sun, of course, the hydrogen bomb, first demonstrated in 1952. And here, a little more recently, TFTR, the tokamak fusion test reactor from Princeton, back in the 90s, set multiple records for controlled fusion. Didn't quite get to energy gain, or really not very close at all, but it set many records that demonstrated controlled fusion is possible on Earth. I also want to talk about some differences and similarities between fission and fusion. I think it's useful. So, of course, as probably everybody knows, fission is the splitting of a radioactive heavy element like uranium. If you bombard it with a neutron, it will create products and more neutrons. This can drive a chain reaction, and that's how fission power plants work, and that's how the atomic bomb works. Fusion, as I already mentioned, is a joining of two light elements. and the reactants carry even higher energy per mass of the reactants. So some similarities with fission, and these are generally desirable things. Minimal end-to-end carbon emissions. It's highly dispatchable, meaning, you can do it day or night, doesn't depend on the weather, doesn't depend on the geography. It's potentially flexible in terms of load following. It's very high energy density, so you don't need to cover acres and acres of land for it. You could site it near population centers, well, at least fusion you can. And it's capable of meeting worldwide power demands, which is really, really a critical need going forward if we're going to drive down carbon emissions. Now, there's important differences from fission, several important differences. There's no long-lived radioactive waste. That's a big, big problem for fission, especially in its perception. There's lower weapons proliferation concerns because it doesn't generate long-lived radioactive waste. Because the long-lived radioactive waste also have elements in it that are used in weapons. So the two are kind of related. It's abundant fuel. There's basically enough fuel, deuterium, in oceans essentially to last for infinity for humanity. And tritium is produced through the neutron interaction with lithium. And mineable lithium may last 1,000 years, but then at that point you could probably mine lithium out of the oceans as well. That will essentially last for infinity for humanity. And it's inherently safer. There's no meltdown risk. So worldwide efforts have been trying for 60 plus years to harness controlled fusion. And this schematic is just to kind of give you a mental image of what it would look like. The main point here is you need to keep the deuterium-tritium up to such high temperatures that it becomes a plasma, a collection of charged particles. And the trick is to hold it there hot enough and long enough that enough fusions can occur to give you energy gain. And you need that energy gain in order to generate electricity. And so this is just kind of a cartoon illustration. You have, if you're successful in assembling the plasma for the duration you need, this could be steady state, it could be pulsed, there's many different fusion approaches, or you need to contain it somehow, and there's this flux of energy and neutrons coming out, so your structure needs to be able to survive that. That's a big challenge of its own. You have some kind of moderator fluid where the neutrons deposit its energy and bleed your tritium, and then the rest of the plant can be fairly standard. I mean, you can drop a fusion core into a coal plant, into a fission plant, and it's a heat exchanger, drives the steam turbines, and you create electricity. So why do we want why do we need or want fusion power? So it's risk mitigation for the near term, if we want to just be soberly honest about it. Part of the problem fusion hasn't gotten the huge amounts of funding is because it's hard to make the case that it's truly urgently needed due to all the other energy technologies out there. What this plot is showing, as probably many of you have seen plots like this, is the greenhouse gas emissions, in this case the annual global amount versus the year. And the international climate panels and such show that it'd be really nice if we could drive it downward in order to keep the global temperature rise to a modest amount. And then you've also seen that the baseline and kind of policies and things are coming really, really far away from what we really, really want. And so the point is, there's this gap here where innovation is needed. I mean, if we're really going to have a chance of achieving this type of performance, what do we need to do? Can renewables alone handle it? Most serious thinkers believe not. If you add advanced fission, that maybe you can do it, but it needs to be deployed quickly, and advanced fission's acceptance is very problematic. And so I see, fusion really as risk mitigation. If we really want to start driving carbon emissions down, we need fusion to work very quickly and cheaply so it'll be adopted. But also, most of you may have heard fusion kind of as a holy grail of energy, and indeed, I think in the longer term, fusion will actually be needed, not just desirable. If we want to do deep decarbonization, we want to generate fuels for transportation, we want to do deep space travel, water desalinization, and even a colleague of mine at Los Alamos is really big on this thing, deflection of extinction level meteor or comet impacts. If you don't detect a comet until very, very late in the game, and the only way to get to send something up to deflect it is with the levels of impulse and thrust that you get with fusion. So, long term, if humanity is going to survive, beyond what we can see, you're probably going to need fusion. Okay, I have a couple of more technical slides, especially for the technical students in the audience. Just want to say a few words. How do you achieve net energy gain via controlled fusion? So this is a well-known bell curve. In this case, if you consider the collection of plasma particles in your system, well, you really wanted to have a bell curve in order to get net energy gain. And the reason is the following. You need to invest energy to accelerate particles to the energies you need for fusion to occur, and I'll get into that in a moment. But you'll scatter the particles some several hundred times before a fusion event will occur. So you can't just simply accelerate a particle, expect it to fuse, release all that energy, and get your energy gain, right? It's going to scatter 200 times. So you need to so if you were to do beam fusion, which is kind of shown like this, if all of your particles are at some velocity, you need to accelerate it 200 times before you'll get a fusion event, and that's very difficult to get energy gain. But if you can hold a thermal population for long enough time, then these tail ions or fuel ions will give you the fusion, but they also scatter, a bunch of times, but they're held in that distribution. So that's how you get energy gain, is to get a population of ions to a fairly high temperature and then rely on these tail ions to give you your fusions, and hopefully a non-ideal effects will keep them there long enough that they can overcome the 200 times scattering before they fuse. Okay, so that's kind of the basic idea of getting net energy gain. Now, I don't want to say beam fusion is impossible, because if you can recover that lost energy, you can still potentially get net energy gain, but it's very, very difficult, and there's really no credible ideas out there for getting energy gain out of beam fusion. Okay, and the other thing I really want to mention is something known as the Lawson criterion. This is a very simple, elegant argument and it's a key metric on the way to commercial fusion power. So basically, you could write down the fusion power and the thermal losses of your plasma as such. This is the fuel density. This is a fusion nuclear cross-section. This is the velocity of your fuel particle. This represents the ensemble average of your thermal distribution. And this is the energy released in the helium piece of the DT reaction. And then this is the thermal energy and the time that you can hold the thermal energy in your plasma. Okay, so there's a lot of complicated plasma physics buried in here. Okay, this energy confinement time is essentially the whole of plasma physics research over 60 years, is how do you extend that, how do you grapple with instabilities in thermal transport to extend this number out. That is the field of fusion plasma physics. Okay, and you can rearrange this and get this nice little relationship. The fuel density times the confinement time must exceed a threshold, and that is the Lawson criterion. So if you plot what this value is over here for different fuels, because different fuels have different nuclear cross-sections, you get these various curves, and you see that the DT curve has the lowest threshold value, meaning it's the easiest to accomplish. It's also occurs at the lowest temperature, which also makes it easier to accomplish. I mean, it's not easy, we haven't done it yet, but it's the easiest. And if you plug in numbers, you get something like this. You need something of order 10 to the 20 seconds over cubic meters at about 10 keV, which is 100 million degrees. That is the Lawson criterion. And there's also another way to express it. If you put in the temperature as well, it's the fusion triple product. And so you generally need something like, you need to hold a plasma at 10 atmospheres for a second. Okay, so it could be 10 to the 9 atmosphere for a nanosecond, or it could be 1 atmosphere for 10 seconds. And that speaks to the variety of fusion approaches you can conceive of, because you just simply need to exceed that product. And so I've already mentioned controlled fusion is difficult. We haven't quite achieved it yet, at least with energy gain. So 60-some years, only 2 approaches today approach these Lawson conditions, and both with a long ways to a power plant even when we achieve the Lawson conditions. So one is something based on a tokamak. It's a toroidal magnetically confined geometry. That's magnetic fusion. There's an international project called ITER being built in France. People generally believe it will show scientific break-even, meaning that the fusion power will exceed the heating power. It won't exceed the wall plug power that you're drawing from the wall, but it'll exceed the heating power. But as you can see, the price tag is big. No one country is willing to take it on do it on their own. The other one is Inertial Fusion, National Ignition Facility in Livermore, California. This facility was built not for energy purposes, but for creating the conditions needed to validate our computer codes that take care of our nuclear stockpile, the nuclear weapons stockpile. So data here is being generated in order to benchmark and validate nuclear weapons design codes. And of course, from Los Alamos, I have quite a bit of intersection with that work. But I also want to point out, there are many credible fusion approaches out there, mostly at earlier stages of development. It's really confusing to people outside of fusion and even to many people within fusion. I made this chart mostly to try to help people understand that there is some method to the madness. I already mentioned earlier, there's thermonuclear approaches that rely on a thermal distribution of fuel ions, and there's non-thermonuclear approaches based on beam-like systems. So that's kind of the highest level of categorization. And then within thermonuclear, you have kind of this longer pulse, lower density, like magnetic confinement, to the pulsed higher density, like magnetized pulsed systems, which I'll talk about, and this is the area that I've worked mostly in recent years, and then also inertial confinement fusion. And then kind of there's a trend toward higher density as you move left to right here, and you may see some concepts in here that you may have come across. And as I already mentioned, energy gain is unlikely or even impossible for non-thermonuclear approaches. But you'll nevertheless see media stories about private companies pursuing some of these non-thermonuclear approaches. And so I also want to mention thermonuclear fusion parameter space. More recently, it's been recognized that you can theoretically get to Lawson conditions over this huge range of fuel densities, everything from 10 to the 14 on up to 10 to the 25 per cubic centimeter. This is like 100 times solid density. So you can see the huge range, and this is well below atmospheric pressure. So it's just a vast, vast parameter space. And this is a little cheeky, but we're plotting the kind of estimated cost of the fusion core depending on fuel density. And the reason there is this dependence on fuel density is because the fuel density as well as the magnetic field really determine the size and the thermal transport rate of your plasma. And so the heating power and the stored energy are are capitally intensive in your fusion core. So what happens is if you're in this middle regime here, in other words, you have a magnetic field that slows down the thermal transport because charged particles spiral around a magnetic field. And then you have the higher density, which means you don't quite, you have a higher density than magnetic fusion. If you remember, the fusion power goes as n squared. So there's an advantage of being at higher density. But to go to such high density means you have to implode the thing so fast that you need a $2 billion laser. That brings the cost back up again. So there happens to be kind of a, what we call a bathtub curve of potential cost. The ITER device is costing tens of billions of dollars. NIF is already built and working. We know that it cost about $4 billion. And the idea is somewhere in here, we hope to find something that cost $100 million or a few $100 million. And with the lower cost, development steps become cheaper and faster. More people are willing to make the investment to do it. And that's the idea. And there's a very nice paper that has the technical details in it, but it's written for a broad audience. And if you're interested in this argument, I'd suggest, I really recommend looking at that paper. I also want to just mention then, so in that intermediate density regime, which I'm calling pulse magnetized intermediate density fusion, there's also several approaches within that regime. One is called Magneto inertial fusion, and these approaches generally have something we call a liner. It's essentially a pusher. And the pusher compresses a magnetized plasma in size. So it goes from, maybe a factor of 10 in size. And because the density and the temperature and the magnetic field will all get compressed, the numbers go up. And so you start with some modest parameters, and by compressing it, you get to fusion conditions. So that's a basic idea of magneto inertial fusion. There's also things called Z pinches, Z referring to the axial coordinate direction. But here, and this was kind of the earliest, simplest known way to get toward fusion conditions, you simply run a huge amount of electrical current through a gas, and this is what Professor Hammer's group does. Then you squeeze the plasma because it generates this azimuthal field, and the azimuthal field provides a pressure that compresses the plasma. The challenge here is that there's all sorts of instabilities driven by that current. And the thing, even though it's very effective at compressing it to high densities and temperatures, you can't keep it there long enough. That tau E parameter is not fulfilled. So early work in this area, or most work in this area, has very little prospect of getting to energy gain. But there are new, in fact, the star result of the ARPA-E program is based on a variant of the Z-pinch. It's a stabilized Z-pinch, and hopefully I'll get to talk about that a little bit. So let me move to the next piece of the talk, the status and remaining challenges for fusion. So this is exciting. We are on the cusp of demonstrating fusion energy break-even from a technical sense. If we rely on ITER, we're still decades away, even though we think we know how to do it. And this is what I'm calling the Kitty Hawk moment for fusion. If we can demonstrate that, really the floodgates and I think societal interest will exponentiate. So this is that loss. This is the triple product, the n tau t, right, in atmosphere seconds, and versus historical progress in fusion. And so you see from the late 60s, when the Russians revealed that they had something called a tokamak that had 10 million degrees temperature, all the way up to the late 1990s, where we were on the cusp of scientific break-even. There was rapid and really impressive progress. And this exceeds Moore's law. There's a lot of plots out there you'll see that plots Moore's law, and it's actually slightly lower than the progress made in the triple product. So the reason fusion gets a knock is because we don't have a product. But the progress made scientifically is truly, truly amazing. But here's the problem, right? Based on the tokamak, it's become so expensive. That's partly what is causing this delay. The other piece is that because it's so expensive, you need 9 countries, to participate, and that just becomes a sociology and political problem. If one country were willing to do it, you could probably cut this time in half or more, and the cost too, probably. But here's a picture of the tokamak. This is being built in France. If you're interested, Google ITER, and you'll see some images of it going up. I mean, it's a shrine to humanity, the size of this thing, and that's why it's taking so long. So I kind of already got to this. Why the delay? And there is growing interest and urgency and impatience, not only with the fusion community, but with the entire rest of the fusion ecosystem about trying to do something about this delay. You know, we think we know how to do something about it. There's no slam dunks, but nobody wants to sit around and wait for this. This will just be too late to have any impact this century, because beyond this is another step even bigger. And despite that, the European Union and China are making plans to make the even bigger device, and who knows where that sits on this curve. Lyndon.
Can you say a word about the point to the left of ITER? So is that an ITER point also at a different point of its evolution, or is that a different technology?
This one?
Yeah.
This one, it's based on a tokamak. It's not ITER itself, but it's based on a tokamak. And these highest points are from the TFTR points of the 90s, as well as a jet tokamak in the UK. And that's where essentially, I mean, we've done a tremendous amount of scientific understanding of the tokamak since then. You know, we're kind of here now, but we haven't fielded an experiment trying to push that by itself because of the cost. So progress has been great, but so are the remaining challenges. And I just want to summarize the list here, maybe, and then try to spend about a slide on each of these. So the first is to achieve a burning plasma. That's really the next step, and I'll talk about that. And then if we were able to do that, we want to demonstrate controlled wall plug energy gain. This is ultimately what you need. In other words, the energy you draw out of the wall to run the system needs to be smaller than the actual fusion power. And at first, you want to do it for a short duration. And then you want to contain the fusion plasma. I already referred to that. You want to be able to extract the heat and achieve a closed fuel cycle, in other words, the tritium breeding. And you need to do this in a way that extends to very high duty cycle operation, right? For a power plant, you can't just pulse it and then leave it there for 3 days and then do another pulse. It's got to be on like 90+% of the time. And when you do that, so while you can do short durations without major material advances and other technologies, for high duty cycle operation, you have to have these advances in order to contain the fusion plasma. And then finally, as if that weren't enough, you have to do this in a way that scales to economical fusion power. Otherwise, nobody's going to use it, right? At ARPA-E, we have this saying, if it works, will it matter? So even if the ITER path does all these things eventually, it probably most likely will not satisfy the last piece. And so you're going to end up, you know, with a shrine to humanity. So challenge 1, the burning plasma. In fact, I want to mention this National Academy's report that just came out, and I'll say a little bit more about that toward the end of the talk. But the burning plasma is the next scientific step for fusion energy development. I already put this equation up earlier for the Lawson conditions. This was the fusion power has to exceed the thermal losses. And so for a burning plasma, what happens is that the power from these charged fusion products, represented on this side, not only does it have to exceed the power losses, it has to really dominate over the recirculating power. By recirculating power, I mean like your heating power and the power that you're using, you know, to generate, you know, your not only your auxiliary heating, but the magnet systems, et cetera, right? Now the problem here you can see is while you might be able to cross this threshold for a moment, because your fusion power is so dominant here, well actually that's the next slide, so let me move through that. But we still have to do this piece. Once you do this piece, you need to get to a high enough energy gain in order to have a power plant, right? Not only does the fusion power you generate have to run all the systems and heat the plasma, you also have to put enough power onto the grid to make a profit out of it, right? Which is very demanding. And generally, what you want is something like the fusion power over all of your input power, not just the heating power, to kind of approach a factor of 10 or so. I mean, it depends on the different approach. It depends on how much energy recovery you might do. But it's of that order. One is not going to get it, is not going to do it for you. And so when you're dumping this much fusion power into your plasma, you can imagine that this becomes a control problem, right? I mean, how do you control something with 1/10 or 1/100th of the energy that's being just piled on there. And that's actually a substantial risk. So for the tokamak development path, that risk is not publicized very well. It's possible that we will never be able to do that, is control a plasma that is dumping all that fusion power in. So the next step beyond demonstrating burning plasma is to demonstrate that you can control it for the energy confinement time, right? Otherwise, you are not going to get a power plant relevant gain. I kind of lumped up together these third and fourth challenges. The engineering, the interface between the fusion core and the balance of plant and closing the fuel cycle. So I've just kind of crudely drawn a box here. We need to engineer this box, which we do not know how to do today. Not only the advanced materials that can handle the neutron flux, but also the tritium breeding systems. If you're successful in breeding your tritium in this moderator fluid, that moderator fluid is going to head out toward your heat exchanger. So now your heat exchanger not only needs to exchange a heat, but you need to somehow process the tritium out of there. You need to process and extract the tritium. The tritium is a hydrogen. It's going to just want to permeate through everything. You can't tolerate that. If it permeates into the environment, the regulatory agencies are never going to let you build this thing. So this is a lot of chemistry, chemical engineering. This is a lot of material science, maybe even nano structuring of materials, additive manufacturing. So there's a lot of interdisciplinary forefront fields that are needed to engineer that box. Finally, if fusion works, will it matter? This is a very interesting study. The reference is given here. People have asked the hypothetical question, what capital cost of construction is needed for a hypothetical zero carbon, 100% capacity factor source to be adopted quickly? So this is not even a fusion specific question. This is just generally, if we had such a power source, how cheap does it have to be to displace fossil fuels, especially cheap natural gas? Well, here's their answer. And of course, all these things are fraught with uncertainty. But if you plot the fraction of zero carbon generation as of the market size versus the capital cost, the capital cost is low on the right side here, so it's a little tricky. So you see at about $3.6 per watt, you may start to displace legacy fossil fuel generation, meaning retiring power plants, right? But it's not going to, natural gas, combined cycle natural gas is still cheaper than that, so you're not going to displace that. But at $2.2 a watt, you may even start to displace cheap natural gas because of the zero carbon advantage and other advantages of fusion. So this is a very demanding, for you guys who may not necessarily appreciate these numbers. I mean, right now, if we were to project a power plant based on like an ITER technology, again, there's uncertainty, but it'd probably be over $20 a watt or not more. So it's just, nobody's going to build it. And advanced fission, and fission in general is already proving that. Fission is something that works. It has some disadvantages, of course, compared to fusion. But at $10 a watt or more, nobody is building fission plants. In fact, they're turning them off, even the good ones, which is a problem for driving down our carbon emissions. So how do we realize commercial fusion power soon enough to make a difference? So fundamentally, we need societal pull and technology push to really accelerate fusion development. And the societal pull ultimately, I think, has to come from a recognition of these three things, or a commitment to these three things. Decarbonizing our electricity generation. And what this does actually is it allows all sorts of other things, creating synthetic fuels for transportation, electrifying the transportation sector, but it all starts here. If you don't decarbonize your electricity generation, doing all those other things may not even help you, right? We need to ultimately enable deep decarbonization. The US, well, I'll get to it, so I'll get to that point later, so I won't talk about it now. And then also recognize that world and not US markets really drive the urgency of the problem. a lot of the energy R&D policy in this country is being driven with a focus on U.S. market needs. But the U.S. market is not, the U.S. energy production market is not what's going to drive carbon emissions in the world, right? I mean, it's U.S. production got us to where we are today. But places like China and India and other developing countries are going to drive the carbon problem going forward. So we really need to pay attention to what the world market needs and how and what technologies will be adopted quickly in the world market. Technology push. So, you know, I've mentioned kind of what we're focused on, this ITER development path that might lead to something in the late part of the century, and it may or may not be economically viable. It's just not going to affect the urgent problems of this century. So to get over that, there's kind of two strategies that have been seized upon by the fusion community, especially privately funded fusion companies, which I'm going to get to. It's a very curious phenomenon. We want to aggressively develop innovative fusion concepts with high potential for economically competitive power plants. That earlier zoology chart of fusion approaches I showed you, well, many of those approaches were conceived of because they were inherently more attractive if you could get the n tau T high enough. The problem is the n tau T is not high enough, but no work is being done to make them, you know, to improve them. So this is my particular focus at ARPA-E, is to tackle this first piece of it. And then secondly, leverage technology advances to transform fusion attractiveness and development across all fields, but in particularly the tokamak. So things like advances in materials, advent of high temperature superconducting magnets, you know, use of machine learning and exascale computing to, you know, to really fundamentally improve your development cycle and lower the time of the development cycle. All these things can even make the tokamak possibly of interest in terms of economic viability. And two private companies are actually taking this strategy. One is Tokamak Energy in the UK. They're doing this for a spherical tokamak, kind of a compact tokamak. And then more recently, an MIT spin-out called CFS, Commonwealth Fusion Systems, has really upended the conversation in fusion because they're coming out of the MIT Plasma Science and Fusion Center, which has been funded by DOE for decades. And you know, most of these other private companies are up in this space, and the main fusion community has been, you know, hasn't paid as much attention there, and because they're not as far along. But because MIT has come into this argument, suddenly everyone is taking notice, and I think it even drastically influenced the National Academy's recommendations. So let me just say something about the societal pull. Kind of already alluded to some of this, but decarbonizing electricity production as a first step toward deep decarbonization. So this is plotting this is again just the U.S. market, but like I said, we should really pay attention to the world market. Total power reactor power sector generation. Okay, in this case, it's billions of kilowatt hours versus the U.S. And all these different pieces of the bar charts represent, you know, coal. You'll see was pretty big. Natural gas, you see, was hugely growing in recent years, and that was pushing down the coal. This is why U.S. carbon emissions have actually been dropping. It's because natural gas is lower carbon emitting than coal, and it's the rise of natural gas that's actually pushed down the carbon emissions. But you see that it's going to saturate. Natural gas alone is not going to drive the coal to zero. So we're probably kind of almost as low as we can in carbon emissions. The new capacity is going to be met with renewables, but renewables is likely not going to grow fast enough to drive the coal to zero. And so advanced fission and advanced fission technically could drive coal to zero, but there's socio-political problems that are capping fission, right? It's too expensive, the public fears it. There's a lot of problems that go beyond the technical realm. So it's not likely to drive down coal to zero. So as I mentioned earlier, if we can get fusion to work quickly, kind of in this time frame, and get it to penetrate the market quickly if it's cheap enough, then maybe we can start driving down that coal to zero. And I think this problem becomes much more dramatic if you look at the world market demands. Okay, so a couple words on the technology push. We would like to aggressively develop high potential innovative fusion concepts and reduce the size and cost of tokamaks, as I already alluded to. So just showing one example of a high potential innovative fusion concept. This was one of the concepts funded by ARPA-E in its first fusion program. This is something called a shear flowed stabilized Z-pinch. And as you see, this thing is tiny. It's the size of a human, right? And so these are two metal electrodes. And if you puff some neutral gas in the back and discharge this capacitor bank, you'll drive a current down one electrode across the gas, which becomes a plasma, and back on the other electrode. And through electromagnetic forces, it accelerates out, it collapses into this pinch. But there's a gradient in the axial velocity, a dV/dr. And that dV/dr actually stabilizes all the bad instabilities in the Z-pinch. And so they've actually, as part of the alpha program, so to be fair, this concept was studied over many, many years at a low level, more like a science experiment at the University of Washington. But it was ARPA-E that came along and allowed them to push their current to the point now where they're approaching fusion conditions and generating neutrons. Now, of course, there's going to be issues as you increase the current to the point of break even. The electrode erosion becomes severe. There may be new instabilities that develop, almost certainly, but it remains to be seen. But the point is, for a few $1 million that ARPA-E put into it, they were able to, improve the fusion triple product of this approach by a factor of 50. And we need, if we're going to drive the attractiveness of fusion, we can't leave any stone unturned. Any credible approach for a few $1 million investment that has the potential of climbing up that triple product curve, we need to unturn all those stones, because we need a lot of shots on goal, I think, to have an attractive final answer. And this is kind of the star result of the alpha program. This is high temperature superconducting tape. It can create very high field and it's superconducting at higher fairly high temperatures, like even 50 or 70 Kelvin. And what that does is it dramatically allows you to reduce the size of a tokamak because of the higher field. But secondly, with low temperature superconductors, you can't have a joint. There's just not enough thermal capacity at those low temperatures to prevent the magnets from quenching. However, at these higher temperatures, you can allow a joint, and that allows you to take the tokamak apart in half. And that may sound trivial, but by doing so, you actually dramatically change the maintainability of the tokamak. Now you can immerse it in a liquid metal instead of having a solid first wall. Your solid surface can now be changed out. It doesn't have to last 30 years like you did before. So some relatively mundane features enabled by high temperature superconducting magnets suddenly might reduce the cost of a tokamak by a factor of 10 or even 30. And that's the approach of the MIT spin-out. But this takes a lot more capital cost to pursue still, even though it's cheaper than ITER. I also want to mention the ARPA-E Alpha program. As a case study on how to move the needle in fusion research with very targeted investments, I gave the example, of this approach as one of the Alpha projects, but the Alpha program focused on this intermediate density regime. It funded several different, a portfolio of approaches, really. The plasma liner one was the one that I led as an ARPA-E researcher. And, you know, with a small investment, 30 million over 3 years, right? That's 10 million a year compared to a $500 million a year fusion program budget in this country. We were able to have, you know, a 50-time increase in the triple product of at least one of these concepts. There were new driver technologies demonstrated that can enable other potentially interesting concepts. And we also leveraged existing experimental platforms like the LLE Omega Laser Facility in Rochester, you know, to quickly study important scientific issues, right? We're not waiting around to build a big device to study the science. We're trying to use facilities out there already, and including Professor Hammer's device. These devices in operation already should be harnessed to really you know, address the scientific issues in a focused manner. Okay, so, and let me move to notable developments across the fusion ecosystem. So these are kind of less technical arguments, but what's happening in the world that's making this an exciting time for fusion? There's a confluence of events that provide an opportunity for somebody to seize on aggressive fusion development, and hopefully even our national fusion program. So there was this just completed National Academy study that I mentioned. It recommends a bolder national plan for fusion development. I'll say another word about that. There's multiple pieces of legislation from Congress that have recently been signed into law. And they instruct the DOE to enable public-private partnerships to develop commercial fusion power. There's a growing recognition by climate foundations, strategy groups, and investors that fusion should be part of a broad clean energy solution, even though, you know, there's still a lot of work to be done to demonstrate fusion. And there's a formation of a Fusion Industry Association, FIA, consisting of more than a dozen privately funded fusion companies. I mean, this alone, the fact that there's so many privately funded fusion companies out there is a really curious thing. So first, the National Academy's study recommends a bolder national plan for fusion energy development. It says specifically, this is one of its 2 high-level recommendations. It should start a national program of research and technology leading to the construction of a compact pilot plant that produces electricity from fusion at the lowest possible capital cost. The words compact and lowest cost are a profound departure from our present program emphasis. And so it remains to be seen how this recommendation is implemented, but it is a big opportunity that we as a community need to ensure is implemented. There's 3 pieces of legislation that will help private sector develop fusion. I'm not going to have time to mention the specifics, but for those interested, I'd be happy to talk about the details. But you can look up these numbers and find the law online. And also contracting mechanisms and IP agreements between DOE private companies. There's a desire to streamline those things because private sector really needs to own the intellectual property if they're going to jump into this. And then I mentioned these strategy groups, foundations, and investors. So here's just kind of a picture of three. This is an investor, venture fund that focuses on private fusion companies. And this is more of a foundation. They want to bring philanthropic money to the development of fusion. So not just public-private partnership, but public-private philanthropic partnership. And then Pegasus is kind of more of a consulting firm. They want to, the champion of this is kind of went through the whole solar field back in the 90s. She has experience on how to engage a broad group of people to enable a whole energy sector, and she wants to bring her experience and expertise to teach fusion people how to do that. And then I mentioned this FIA, recently formed and is poised to spearhead and benefit from this confluence of events. This is the collection of privately funded fusion companies that's part of this FIA. And just 2 days ago, I was in Palo Alto, California. The FIA hosted the first of a investor breakfast series where we invited Silicon Valley venture capital investors to come learn about fusion, opportunities and risks. So this was a panel discussion with a fusion entrepreneur from General Fusion. This is somebody from EPRI, the Electrical Power Institute representing utilities, myself representing federal perspective, and this is Ray Rothrock, who is a venture capital a person who helped raise $500 million for Tri-Alpha Energy. So that was the main part of my talk, and Dave tells me I have a minute. ARPA-E is an agency of DOE. It provides R&D for high-risk, high-reward transformational ideas. And these are the problems ARPA-E is trying to solve. Mainly, I want to get to this point. ARPA-E is about its program directors. It's not like other agencies. People like myself come to ARPA-E. We do deep dives into fields, find white space, in other words, things that aren't being done, and formulate a program based on that deep dive identification of white space that can potentially disrupt and transform a field. That is the congressional mandate of ARPA-E. But not only, so program directors are generally mid to late career people who have established scientific and engineering credentials behind them, and they are thought leaders in their field, and they believe that they can come and start a research program that will transform their field. Those are the people we're looking for. So professors are great, national lab scientists, et cetera, even people from industry, who have led R&D programs at private companies. And so with if it works, will it matter? We focus on market aspects of the technology right from the get-go, so we don't do anything that won't matter. And then finally, we have fellows. These are like postdocs. If you're a graduating PhD student and you would like to do your own deep dive into energy questions and sectors, you have complete freedom to do what you want there in terms of these areas, but generally, if you align yourself with a program director, you can have the most impact. I want to mention the annual Energy Innovation Summit of ARPA-E. This year will be in July in Denver. This has become perhaps the world's most sought after energy innovation event. The main point here is to showcase ARPA-E teams and their technologies, but it draws policymakers, media, investors. It's the entire clean energy ecosystem that shows up to these things. And I'll just close with this. There's a student program centered around the annual summit. I believe the application has been extended to March 8th, so there's time. I will make these slides available so you have this information. But if you're interested in entering the energy sector after you're done with your student studies, this is a great way to make connections and see a broad swath of energy, clean energy development. And so with that, I will end.
We do need to let our students evaporate if they need to. Those of you who have a question, why don't you come up to the front and we will see about addressing them. And those of you who signed up for the lunch after this, it's in